Okay, so chapter 10 is a unit on gases, and I think what you'll find is there's not much new here versus what we did in Honors Chem, so you'll find it to be pretty easy. It's kind of a review of gases and stoich and some other things. A little bit of an expansion. So you know gases, unlike liquids and solids, they expand to fill their container. So if I have gases in let's say in a vial, and I open the lid, the gas is going to come out. It's going to fill whatever boundaries are around it. Okay. We know gases are highly compressible. I can take a balloon and I can squeeze it because the particles of air are so far apart that I can make them come closer together. And for the same reasons, they have very low densities, so not much mass per unit of area, which is why gas densities are typically expressed as grams per liter as opposed to grams per milliliter, which is more typical for solids and liquids. So when we're doing problems, make sure you recognize that the units are likely to be different. So you really can't talk about gases without talking about pressure. So as you know, pressure is the amount of force applied to an area. So it's simply force over area. And what we have is this force of the atmosphere pushing down on us. And the closer we are to the center of the Earth, the further this atmosphere, this column of atmosphere is above us, and therefore more pressure. So you're high up in a mountain, you're going to have a lot less pressure than you will down at the bottom of a valley. So pressure units are, if you think in terms of physics, it's some unit of force over some unit of area, and typical would be newtons per meter squared. Doesn't usually work that well for chem, so there's newton meter squared. Newton per meter squared has another unit that is equal to that, and that's a Pascal. Usually when we are talking about gases, we tend to use several different units, and these are all units at STP, and STP assumes 0 degrees C or 273 K, and unlike standard conditions, which we talked about when we talked about thermochemistry and thermodynamics, that was 25 degrees C. That was more room temperature. This is colder conditions. Okay. So all of these things are equal, 101.3 times 10 to the 5th pascals. The actual scientific standard, the SI units, are 101.3 kPa. 760 millimeters of mercury is also 760 torr, and 1 ATM. We tend to use mostly ATM, and what you'll find mostly on the AP exam is ATM. But you are given problems where you're given torr, and you have to know to make a conversion. Now you do have these units given to you on the equation sheet, but you will not have them for the multiple choice. So you should know these. You should know these four. 1 ATM is 760 torr. A torr is the same size as a millimeter of mercury, and the SI units is 101.3 kPa. Alright, so let's do a little bit of conversion. A is convert 0.357 atmospheres to torr. So if I have 0.357 atmospheres, what I know is 1 atmosphere is 760 torr. And if I punch that into my calculator, I get 0.357 times 760. Should have 3 sig figs in my answer, and I get 271 torr. If I'm doing this part B here, it is convert 6.6 times 10 to the minus 2 torr to ATM. What I know is 760 torr is 1 ATM, and if I punch that, I'm going to get 6.6 second EE negative 2 divide by 760, and I get 8.7 times, looks like I want 2 sig figs, 8.7 times 10 to the minus 5 ATM. And lastly, I have 147.2 kPa, and what I know and I want to convert it to torr, and what I know is 101.3 kPa is 760 torr, and if I calculate that, I get 147.2 times 760 equals, divide by 101.3, and I get 4 sig figs 1104 torr. Okay. Let's talk a little bit about how pressure is measured. We talked about the barometer in Honors Chem. It measures the pressure of the atmosphere, and what a barometer originally was this pool of mercury. Mercury is very, very dense. Pool of mercury. There's this tube, and there's mercury that can rise in the tube, and the pressure from the atmosphere pushes down on this surface of this mercury in the tube, and depending on how much pressure there is in the atmosphere, it will push either more or less mercury up the tube. And the distance that mercury rises is expressed typically in millimeters. And so the pressure is simply a measure of the height that the mercury goes up. Manometer is used, or has been used in the past, to measure the pressure of a gas. It works similar to the barometer. Here I have a vessel where I have a gas in here. Usually a gas is being created in a vessel, and this gas can move and exert pressure, again, on a column of mercury that's in this U-tube. At the same time, the gas is exerting pressure in this direction. The pressure from the atmosphere is pushing down on the mercury, and it's kind of a battle. Let's see who has the higher, can push the mercury higher. And so we usually assume 760 millimeters of mercury, the pressure in the atmosphere, plus the height, if it's 760 or whatever it is, plus the height difference. And you got to think about which one has higher pressure, and you got to know whether you're subtracting or adding the pressure from the manometer. So in this case, the gas is pushing the level of the mercury higher up than the atmosphere can push the mercury. So let's take a look at how we solve a problem here. Okay, on a certain day, the barometer in a laboratory indicates 764.7 torr. A sample of gas is placed in a flask attached to an open-end mercury manometer, shown in this diagram. A meter stick is used to measure the height of the mercury above the bottom of the manometer. The level of mercury in the open-end arm of the manometer has a height of 136.4. 136.4 here, where the mercury in the arm that is in contact with the gas has a height of 103.8. And these are both millimeters. What is the pressure of the gas? So the pressure of the gas is going to be whatever the pressure of the atmosphere is adjusted for this difference. So the difference here between 136.4, let me see, 136.4 minus 103.8 is 33.4 millimeters. So that's an adjustment to the room pressure, and in this case the gas again is pushing the mercury up higher than the atmosphere is, so we're going to add that to the pressure in the room, 33.4, and when we do that we get 798.1 torr. Wants the answer in atmosphere, so I'm going to take that 798.1 torr, and what I know is there are 760 torr in 1 ATM. So if I punch that, I get 98.1 divide by 760 760, and I get 1.05 ATM. And I can do the same thing for part B. We want the answer in kPa, so 798.1 torr, and there are, let me see, 760 torr is the same as 101.3 kPa, and if I punch that, I get 798.1 times 101.3 equals, divide by 760, and we get 106.4, a little bit off, but good enough. kPa. Okay. Alright, so let's talk about the gas laws. So we had several gas laws we learned about in Honors Chem. Boyle's law is the law that says a volume of a fixed quantity of gas at constant temperature is inversely proportional to the pressure. Okay, so there is the relationship between pressure and volume. And what we know is that if I have a gas and I compress it, so I have the same number of particles moving at the same speed, they're going to make more collisions with the side of the container, and if they make more collisions, the pressure will go up. So as volume goes up, pressure goes down, or as volume goes down, pressure goes up, as we would expect. And what you need to internalize right now is that the pressure of a gas in a closed container is strictly based on the number of collisions with the side of the wall. It's not collisions with each other because there's so few gas particles compared to the surface of the wall, but it is the collisions of the gas particles with the container. Okay? So if I have more space, more wall, same number of particles moving at the same speed are going to hit less frequently. So if you were to plot pressure and volume, you get this graph right here. As pressure increases, volume decreases. If you plotted pressure, volume versus 1 over pressure, or pressure times 1 over volume, either way, you get a straight line. Okay, so pressure is directly proportional to 1 over V. It is inversely proportional to V. Okay? So Charles's law is what we're talking about there is volume versus temperature. And what this says is if I increase my temperature and I keep my pressure the same, my volume is going to increase. So here I have a moving piston. I heat this up from 23 to 327, and as a result my particles are colliding more with the side of the wall, causing the volume to go up. Okay? I can also say that the temperature, I can look at pressure versus temperature, and if I increase the temperature and keep my volume constant, the pressure will go up, right? And you can see we're trying to keep the same number of particles, and we are simply making these whooshies, or these tails on this longer, to indicate that I'm moving faster. If I plot Charles's law, it gives me a straight line between temperature and volume. If I just plot volume and temperature degrees C, I get a line like this. It does not go through the y intercept, the 0, 0, and that's because in order for volume and temperature to be directly proportional, I need to extend this line to where it hits the intercept, and when I do that, I get this point of minus 273 degrees C, which we know as 0K or absolute 0. And this is known as the temperature at which particles no longer move. Particles don't move. And we know particles always move, so this is a theoretical temperature. We've gotten close to it, but never actually there. So this is a point where I have no temperature, which means particles are not moving, and it is also, because it's sitting 0 here, this is 0K and 0 whatever volume units I have. It's also saying that I take up no space, and we know matter takes up space. So this is the theoretical lowest possible or below possible temperature. So if I plot volume versus temperature K, I get a line that makes the relationship directly proportional, and it goes through 0, 0. So if I double my temperature K, I double volume. Don't have that same relationship here between volume and temperature C. As I increase temperature C, I increase volume, but it's not directly proportional. You can see back on this diagram here we are doubling, going from 300K to 600K. Here it is directly proportional, so if I double my temperature, I also double my volume, and that's what you see happening here. Okay, but the temperature went from 23C to 327. I've got to get it in Kelvin to see whether or not I can make that assumption about doubling or tripling along with the temperature. Alright, so we're just talking about these so you can make sure that you can internalize. So Avogadro's law says that if I increase the number of particles of a gas, then the temperature, the volume of the number of particles will go up, or the pressure will go up. So if I have let's say I have this container here, right? Let's say there's a plunger on it, right? And I hold the pressure constant, or let's say I hold the volume constant. Don't let the cylinder move. I through some injection port, I add another set of particles, same number of particles. What's going to happen is my pressure is going to go up, right? If I'm keeping it the same volume. If I let the piston move, as I add more, and I want to keep the pressure constant, then the volume of the container is going to go up. But what I have here is if I have twice as many particles in the same amount of wall, then I have twice as many collisions. So if I double my number of particles, then I double my pressure, or I double my number of particles, I double my volume. This assumes constant volume, and this assumes constant pressure, right? Alright, so let's take a look at a couple of examples. Suppose we have a gas confined to a cylinder as shown. Consider the following changes. Heat the gas from 298. So A is we go from 298 to 360 K in both cases, while maintaining the position in the shown in the diagram. So, and what we want to know for each of these is how these changes will affect the average, let's say the average distance between particles. Distance between particles. We want to know pressure of the gas, and we want to know moles of the gas. So here we got the three things we're looking for. And if it's A, where I am increasing the temperature, here I'm assuming A, because it says the piston needs to stay, volume is constant. And if volume is constant, the average distance between particles, assuming I have the same number of particles, is going to be equal. I haven't added any more particles to the mix, so I have an equal number of particles. But what does go up is pressure, because I had particles with, let's say, a certain size whooshy hitting the walls at a certain rate, but if I have those same particles now moving much faster, they're going to hit the side of the wall much more often. Alright, for B, it says if I move the piston to reduce the volume from 1 to 0.5 liters. So here I'm assuming the same number of particles. I'm assuming I bring the piston down halfway. Okay, so if I bring the piston down halfway, my number of particles is still the same. I have the same number of particles in a smaller space, so the distance between the particles will go down. And because I have less wall to collide with for the same number of particles, my number of or my pressure is going to go up. And for C, it says inject additional gas through the inlet. Okay, so if I just inject more gas, I got the same amount of space, and I am adding a whole bunch more particles. The distance between the particles will go down. The number of particles will go up, and if I have more particles per area or per volume, I'm going to get more collisions and therefore more pressure. Okay, if I initially have a gas at 12 atmospheres in a volume of 23 liters and a temperature of 200 K, then I raise the pressure to 14 atmospheres and increase the temperature to 300 K. What is the new volume of the gas? Okay, so lots of different ways to attack these gas law problems. You know, you can do potatoes and vegetables on the table is equal to potatoes and vegetables on the table. So these are initial conditions, these are the final, and solve. What I like to do is, as my kids from last year know, is I like to make a table where I put pressure, volume, and temperature. I put my initial values and my final values and just kind of think through it rather than trying to memorize equations. So initially we say we have 12 atmospheres. I'm just going to say atmospheres here. We have 23 liters and a temperature of 200 K. Whoops. 23 liters, and this should be, let me try to erase that. That's 200 K. I raise the pressure to 14 atmospheres, increase the temperature to 300, and the question is what happens to my volume of my gas. So I'm trying to figure out what happens to volume, so I start with my volume, and then I think through what kind of factors I need for pressure and temperature. So if I increase, my pressure goes up. If I increase my pressure, it's going to make the volume go down. Okay, so I need some pressure factor that makes volume go down. So I'm going, which would be either 12 over 14 or 14 over 12. So I'm going to use 12 over 14 because that will make the volume go down. So it's 12 atmospheres over 14 atmospheres. And here my temperature is going up, and if my temperature is going up, my volume will go up. So I need a factor, either 300K over 200K or 200K over 300K. What makes it go up is 300K over 200K. Okay? Now I punch that, I get 23 times 12 times 300 equals, divide by, whoops, let me just go back. I put divide by twice. Divide by 14 times 200, close my parentheses, and I get 29. Let me see, I want just two sig figs, so it really should be 30 liters. 30 liters, right? Alright, I have 2.9 liters of a gas at a pressure of 5 atm and a temperature of 50 C. What will the temperature of the gas be if I decrease the volume? Okay, so let's make a VT table. I start my initially and final. I start with 2.9 liters. I'm just going to put liters here. I have atm here. I have 5 atm. And my temperature is 50 C plus 273. As you know, you got to use Kelvin. That's 323 K. Okay. And what will the temperature of the gas be? I'm trying to find new temperature. If I decrease the volume of the gas to 2.4 liters and the pressure to 3 atmospheres. Okay, so I'm trying to adjust temperature. 323 K times something. Alright, so let's think about pressure first. So if my pressure goes down, it's going to be because my temperature goes down, so I want a factor that makes my temperature go down, so it's going to be 3 atmospheres over 5 atmospheres. And if I want my volume, let me see, my volume is going down. If my volume goes down, it's going to be a result of the temperature going down. So again, I want to make this go down, so it's going to be 2.4 over 2.9. And these are both liters, right? So I'm going to take the 323 times 3 times 2.4 equals, divide by parentheses 5 times 2.9, close my parentheses, and I get, Alright, so that didn't work out. Let's try that again. 323 times 3 times 2.4. Whoops. It's always easier to punch this with the finger than it is with this pen. 2.4 equals, and I'm going to divide that by 5 times 2.9. Close my parentheses, and I get 160K. Good. And I want 2 sig figs, so that's just perfect. Alright, a gas has a volume of 28 liters, so I have volume, pressure, temperature. It starts with 28 liters. Temperature 45, so it's 45 plus 273, that's 8. That's 318. Oops. 318, and that's K. I have, it has its volume increased to 34 liters. The pressure initially, I don't know. Unknown pressure. I'm trying to find initial pressure. If I measure the pressure after the change and it's 2.0, and the temperature goes down to 35, so that would be 308 K, right? Alright, so I'm trying to figure out what happens to pressure, or what happened to pressure. Where did it start? So you got to be careful. And this is ATM, right? So if my pressure, if my if my volume went up, that would make my pressure go down, which means I would start with a higher pressure. So I want a factor to make this go up, 34 liters over 28 liters. Okay. Now my temperature went down, which would make my pressure go down, so I also want a factor to make this go up, because I must have started with a higher pressure. So that'd be 318K over 308K. And if I punch all this, I get 2 times 34 times 318 equals, divide by, in parentheses, 28 times 308, close my parentheses, and I get 2.5. Looks like I only want 2 sig figs. I got 2 sig figs and a lot of these. 2.5 atmospheres. Alright, we're going to stop right there for now and come back and talk about the ideal gas equation.